All right. So after the lecture parts, I think that we can work on some real-world data about Alzheimer's disease. So according to the agenda, we should have some dementia, the, for example, the questionnaire data and the EEG data, so we can phenotype Alzheimer's disease, just or doing a cluster analysis just based on this kind of the data. So that is the main topics we are going to explore today. So before that, I want to just give you a very brief summary of how we measure the brain signals using different kind of tools. So in this figure, I show you that the horizontal axis is the solutions of the in space, and the vertical axis is solutions of the measurements in time. So you can see that the EEG and for example, the electroencephalogram, which is the measure of the scalp electrical activities by the electrodes attached to the scalp, it has a very good time resolutions, but the space or spatial resolution is not good. Okay, and for example, the MEG may have quite a good time and space resolutions, but it can only cover the surface of the brain. Usually cannot reach. We cannot reach into the deeper part of the brain to measure the activity inside just based on the MEG detectors. So these are non-invasive technique, and also including the functional MRI, which is the measurements of the blood flows instead of electrical or magnetic activities generated by the neurons. And it has quite a poor time resolutions, but has a very quite a balanced space resolutions. So the other parts are invasive techniques. For example, we can attach the electrodes inside the brain. Usually we can do this for the patient with epilepsy, to find out which brain region we should remove, or the epilepsy focus. And also we can do the optical imaging and electrophysiological studies. So these are invasive measures. But for the dementia, usually we'll just focus on non-invasive tools such as the functional MRI, the EEG, and the MEG. And there's a different kind of the signal transmission in the brain, and the majority of the signal transmission is based on the electrical activities, which is you can observe when the signal transmit from the cell body to the synapse through the axons, and you will cause a lot of significant action potentials. And if you have lots of the neurons and axons, then you will see a significant changes in electrical activities, even measures on the scalp. Okay, so these electrical activities we can measure in two ways. The first, we can measure directly the electrical activities, but we know that there is a right-hand rules, which is the combination of the electric and the magnetic fields. So we can also, that means that we can also use the magnetic detectors to detect the electrical flow in the brain. So that's why we can not only we can use the surface electroencephalogram, which is the many electrodes attached to the scalp, but we can also use the MEG device to non-invasively detect the magnetic field changes in the brain and to determine the electrical activities underlying that region. So MEG has the higher spatial resolutions and also have very good time resolutions comparing to the EEG. However, the EEG is still quite convenient in the clinical practice, and is relatively very cheap, and comparing to the MEG, it is still very expensive. And just show you that MEG usually we can have higher spatial resolutions, but for the EEG, it is the combination of electric potentials from a large brain areas, so it has a poor spatial resolutions, but somehow we can still use this signal to do some calculations and evaluations. So EEG is still a very important technique that used in the neurology and even in psychiatry. And we have published a paper previously showing that the patient with Alzheimer's disease, it has a very significant EEG slowing according to the severity of the units. For example, this is the EEG, 10 seconds of the EEG in a case of mild cognitive dysfunctions, and this is the EEG in the patients with mild Alzheimer's disease, and this is the moderate Alzheimer's disease. So you can compare to the healthy person, you can see that the frequencies become slower and slower. So that is the one phenomenon we know in EEG in terms of dementia. But in this paper, we show you that there's a different association of the neuropsychiatric symptoms and in relation to the EEG features. So, for example, you can see that the aberrant behaviors and sleep is more associated with occipital electrodes. However, the dysphoria is more associated with the temporal electrodes, and also in other parts of the symptoms. So that's why maybe we can use the EEG and also the Neuropsychiatric Inventory data to find out the clusters of the Alzheimer's disease. And so about the Neuropsychiatric Inventory, it's a questionnaire to cover the delusions, hallucinations, and other neuropsychiatric symptoms commonly seen in the patients with dementia. And so this is quite routine. In the clinical practice, we use this questionnaire to assess the BPSD. And so as I said, that even in mild cognitive impairment, it can have some changes in the mood or other behavioral symptoms. And 95% of the dementia patient will experience PTSD at some time point of the course. So that's why this is still a very important area of research to understand why or how can we treat these people with PTSD and how to prevent people from having severe PTSD symptoms. So the data I will provide today is also confidential data because it is not allowed to give you any link to the real patient case. So these data are strictly identified and delinked, so you are not able to identify these data to a real patients, meaning that the questionnaire, the score here already do some modifications. So it doesn't mean that this data is fake data. It's still the real data, but I just try to do some modifications so you are not able to link this data to the real patients. So that is, even this, the data is still not released to the public, only within the class, okay? So I provide 30 patients with Alzheimer's disease and also specifically confine the case to the mild dementia or mild Alzheimer's disease, which is I have a rating scale 1 in the clinical dementia rating scale. And so in this data, you can see that we have 12 dimensions, including the delusion, hallucinations, agitations, depression, anxiety, euphoria, apathy, disinhibition, irritations, aberrant behaviors, nighttime problems, appetite. If you don't know the abbreviation, you can just look in the previous slide so you can have an idea that how these terms is related to the NPI questionnaires. And in the first columns is the total scores of the Neuropsychiatric Inventory. So I give you this, even only just 30 cases, you can immediately see that even the patient have the same CDR rating, meaning that they are all mild dementias in terms of the cognitive dysfunctions. They have a great variations in the neuropsychiatric profiles, and some have a very severe symptoms. For example, this one has a severe depression and anxiety, but the others may have a relatively low scores or even have nothing in their neuropsychiatric inventory. So because of these great variations, that is show you the importance of finding a solution to find the clusters of these patients. And the first thing we will do is to read data into Matlab. So we can follow the command line in showing in this slide to import the data I provide in the form of Excel file and import the data into the Matlab. So in the first line of the code, we are just use the read table functions, which is I already used this in the regression courses to show you how to read the Excel files into the Matlab as a table data structures. And unfortunately, in the cluster analysis, we need to convert this table data to the numerical arrays. So that's why in the second line, I use the table to array functions to convert the data to the numerical data. And in this second line, I just designate the variable to be the neuropsychiatric inventory, which is NPI. Okay, so let's do this in the Matlab platform, so show you specifically how this will, what's the result in the Matlab. So remember in the slides, I just show you just read, using the read table functions to input the Excel data into the Matlab. So I just can copy this one into the Matlab. So if you already download the dementia underscore npi.xlsx file, then you should be able to use the reader table functions and put into the data. So in the right side, you can see that there's a data variable which is under the table data structures. If you double click on this one, then you will see there are several variables which is about the neuropsychiatric inventory questionnaires, and there are 30 rows here, meaning that there are 30 cases, and the items including the 12 items in the NPI. You can find this in my slides, and there's also total scores. You can see there are lots of variations. So these are the data we will use today. And because I said this for the clustering analysis, you can only accept the numerical input. So I will just put the NPI equals to table to array functions to convert the data into the NPI. So you can see that in the data, the type of the data format is the table. Then when I use the table to array functions, I just convert the data to NPI, and you can see that it converts from the table to the double format, which is the numerical format of the data. So if you double click on the NPI, it just shows you the numbers. There's no rows, columns name or rows name. And the next step is to use the K-means cluster analysis. And the K-means analysis in Matlab is very simple. Just use the K-means functions, and the input is the matrix arrays, which is already converted from the table data. And also, but the one thing we need to know is that we need to designate the number of clusters in the K-means analysis. So remember, in the K-means that we will find out the centroid of the data clusters, then using iterative algorithms that we can adjust the centroid and to find out the real classifications of the data based on the features. So it is very important that we designate a number of clusters, because with the number of clusters we need to randomize the initial locations of the centroid in a data space. So for example, if you designate the number 2 as the k equals to 2, that means we should expect the classification into 2 clusters. So the output is the index of the result of the observations. For example, if you have the 30 rows, then you will return to you the result of the clusters into 1 or 2 based on according to the number of clusters. And if you are not sure what I'm talking about, and you want to know more about the K-means functions, you can simply type the doc here. I just type the doc here and the K-means. So you can just to check the informations of the K-means functions in the Matlab. So here you can see that it show you the K-mean clusterings, and just like you can have a regular syntax here. So here I just use a very regular ones. The IDX equals to K-means x dot common K. You can use different variable names here. You don't have to use IDX, just like I use or in the Matlab. You can name it a clusters or something like else to help you remember what it is about. Okay, so there's a very good examples in the Matlab documentations. So here's, for example, it just show you a Fisher iris data. Then it's a very nice examples in the machine learnings, and then you can use the cluster analysis to find out 3 clusters in these data. And unfortunately, we have a very high dimensional data in our example, so we are not able to just use 2 variables to show you the clusters. But it has a very good example here, so I encourage you to, if you want to explore more options about the cluster analysis. For example, you can define different distance metrics here. In the default is the Euclidean distance, but you can use different kind of the distance metrics to calculate the distance from each data point to the centroid. Okay. Also, there's other functions to help you quickly or do the job more efficiently. So I just leave these to you, and you can find out more details about the K-means. And there's a K-means plus, meaning that you can I already showed you in my previous course, and this is a more efficient way and more reliable way to find the clusters of the data. And so you can see how to do this in the Matlab. Okay, so just according to, you can click on this K-means plus algorithms, then you will see what's the rationale and how to do this in the Matlab. All right. So how about that we just working on the real data right now. So back to our slides, then you can see that we just put the simple command here, just copy and paste into the Matlab, and just close this one so you can have a more visible space in when seeing this course. Then just paste my code here, then you can see the response very quickly. So the here again, as I said, the input is two variables. One is the MPI data, and the second variable parameters is the number of clusters. So you can see the result here. It shows you the 30 index, which is corresponding to the 30 observations or 30 rows or 30 patients in our data, and you will classify these patients into the first clusters or the second clusters. So, for example, the first patient will be classified to the second clusters, and the last patient here show you classified to the first group. So you can see that majority of the cases are in the second groups, and only part of them are in the first group. And I will just show you the problems of the randomized initiation trap. So remember that in the previous course I showed you that the locations of this initial centroid is very important, because that random locations will have a significant influence on the final result. For example, here I just show you that you can type this command again. You can see that, wow, that's the result is totally different from the first round. So you can see that the cluster analysis do not have any prior knowledge that which should be classified as the first clusters or the second clusters. So in the first round, these cases are classified under the second groups, but in this case they will be classified in the first group. So there's no reliable ways if you are just using the Kmeans, then you need other for example, a Kmean plus to derive a more reliable solutions. And also you can note that the results of the clustering is quite different between the first round and second round. If you have time, you can just try to run more times. You will see that the results are a little bit different for each time. So if your data is very clean, actually, which is not possible in the clinical data, but ideally, if your data is clean, then you should have a stable classifications. But this is often not the case in the clinical data. So that's why we need be very careful about the results and the interpretations. And also, you can try to assign different number of k in this command. So in this case, I just using the two clusters, but you can also specify you want to classify the data into 3 clusters or 4 clusters. Then I just show you one of the results I obtained from this round. And for example, in the 3 clusters, you can see that some cases are assigned to the group 3, but majority of them still the 1, and few of them are 2, and some of them are 3. If you want to classify into 4 clusters, and you will see different results. So probably the question in your mind is that, how do we evaluate the number of clusters? And that is the big question, because there's no standard methods available right now to tell you the right answers. What I mean is that there's no golden standards, and there are some metrics to help you determine the number of clusters. But most of time, you need to generate a very reasonable hypothesis that how many clusters you want to see, and that is sometimes really hypothesis driven. But in the statistics, we do have some measures that can help us to quantify the reasonableness of this clustering tree. One of the metrics is the silhouette values. So this is a very difficult word to pronounce. It's pronounced as a silhouette value. Okay. The silhouette value, I just copied this from the Matlab. So silhouette values for each point is a measure of how similar that point is to points in its own clusters. So it measures the similarity of the points within the clusters, and when compared to the points in other clusters. And it defines as the equation is here. And the silhouette value ranges from -1 to 1, and the high value indicates that this data point is well matched to its own clusters, meaning that it has good classifications. And a poor match to others means that the value will be away from the 1. Okay, so that is one of the objective measures that we can use to evaluate the potential numbers of clusters. But like I said, most of the time you will need to generate a reasonable hypothesis that how many clusters should be observed in this data. So that is very important. For example, in the last week, I showed you that for the psychotic spectrum disorders, for example, schizophrenia, bipolar disorders, and schizoaffective disorders, maybe the reasonable hypothesis that we still want to classify this patient into another 3 clusters. But there's no strict the ideas or the guidelines tell you that you cannot classify them into 2 clusters. So just you need really have a good hypothesis and the data and insights into the data structures and data meanings. Okay, so let's take a look at the silhouette plot. So in the Matlab, you can just type the silhouette functions and to give us input. The first thing is the MPI data and also the results of the Kmeans clustering. So in the first line of code, I just do the Kmeans again using the standard parameters, which is number of two clusters, and the data, which is MPI. And the output data here is IDX. So this is the results of the clusterings you already see in the previous slide. So I use these results as an input in the silhouette plot. Then it will show you the result kind of like this one. So you can see majority of the cases in this round is classified into the first groups, and the rest of the cases are in the second groups. And you probably see that, because we have only 30 cases, are these really meaningful? I would say that if you have lots of the dementia cases, you will be able to see a real clusters. But because now we have only 30 cases, I just want you to have a kind of insights into how this is working and to develop ideas on your own data. Okay, so you can see that in this silhouette plot, there we can derive the similarity of each data point to the others within clusters. So, for example, in this classification, it seems that the silhouette scores is quite good because, for example, in the first clusters, most of the cases have um, the values, silhouette values close to 1, and also similarly in the second cluster, the silhouette value also is very high, but there are few cases they have a poor silhouette values. So that might indicate that we have one clusters here, two clusters here, and maybe there are three clusters. So that is one possible interpretations. But again, I want to emphasize that the number of clusters still dependent on your hypothesis. That value is not the solely criteria you should look at. So one of the way to determine the number of clusters is that we just average all this silhouette value across each observations and to see what's the average here. And to do this is very simple because once you have the clustering results and once you have a silhouette the calculations, then you can just average every silhouette value you observe in the data. So for example, in these long several lines of codes, I just calculate the average silhouette values for each k. So for example, the first two lines, I calculate the average silhouette value for the case of the two clusters, and the line 3 and line 4 is the calculation of the average silhouette value for the 3 clusters and etc. So I do this from the 2 clusters to 7 clusters, and you can see that the average silhouette values is going down from the 0.78 to the 0.48. So it seems like the 2 or 3 clusters is still the solutions, and so that's why you really need to look at these values and to determine that which number of clusters is compatible with your hypothesis. So in this case, we might conclude that maybe the 2 or 3 clusters is enough to explain our data. So let's conclude our the calculations about the K-mean clusters. But again, I want to encourage you to look at internet resources about the K-mean and other methods. Then you can have more insights on how to do clustering analysis and how to obtain the more reliable results. Okay. Okay, so the second part of this workshop is to do the hierarchical clustering. So I didn't talk much about hierarchical clustering, but you should have see lots of the dendrogram or clustering trees or phenotype trees in the second part of my course last week. So that, as I said, that hierarchical clustering is more based on the distance and similarities, and we can just visualize that similarity by grouping them into the same clusters or same nodes. So it's also very simple to do this in the Matlab. For example, you can use the distance functions to calculate the distance between each observations, and you can use the linkage functions to measure the clustering patterns of these distance matrix. Then you can visualize this with the dendrogram. So these 3 lines of code just show you how to generate a so-called hierarchical clusterings. So this is the result. So how about I just show you in the Matlab platforms. So here, just copy these three things into Matlab, and so you can see that I'll just clean these screens so you can easily see my commands. I just paste things from the PowerPoint slides, then you will see the results here. So, okay, so the advantage of the hierarchical clustering is that it does not have the randomized initiation trap problems, so the results should be stable with different trials and rounds. But the problems with the hierarchical clustering is that sometimes it does not have a good ability to find out which two items or observations should be clustered into one groups. So that is totally dependent on how you define the distance or similarity. So you remember in the last week I showed you that we already published a unique methods called information-based similarity index, and that we can apply that distance metric methods to different kind of the symbolic data. So if you have a data, you should also think about how to measure the distance or similarity between different observations. So putting that more simply is that if you have two patients, then how to tell that these two patients are similar is very important. Are they similar because of the symptom profiles, or the laboratory test, or brain imagings, or even cognitive functions, or even neuropsychiatric symptoms? That is a very important thing, because the way you define the similarity will determine how you interpret results. So in this hierarchical clustering, you can see that at least for me, it's not easy to interpret result, because you can see there's no clear patterns of classifications that into two major or three major clusters. So that is basically using hierarchical clustering, I can conclude that maybe there's no clustering patterns in this data. But however, I want to emphasize that because I only give you 30 cases or 30 patients of the data, so you should be able to expect that maybe there are really some patterns of clustering if you have like hundreds or even thousands of the AD data here. So there's always a problem is that we need more and more cases in machine learning to find out the patterns. Okay, also there are some considerations about hierarchical clustering, and that is about the linkage functions. And I just, because of the nature of this course, I don't want to torture you on many mathematical details, but I just encourage you to look at the Matlab documentations or internet resources that to understand what is the linkage functions and how does that affect your results. So the two of the important elements in hierarchical clustering is that how you define the similarity, and the second one is how you link two cases. What's the way to link these cases? So that is the linkage function you need to define. So that is both these two steps will affect the results of the hierarchical clustering. So in the final parts of this workshop, I will show you use the very convenient software developed by the Academia Sinica in Taiwan, led by the Professor Chen Ho. So he is now the head of the Institute of Statistical Science in Academia Sinica, and he already developed a very good visualization tools called Generalized Association Plus, which is abbreviated as the GAP. And the software is the Java designed software for the Generalized Association plot and visualization of the data. So you can download the software freely from the GAP website, and you just follow this the web link, and I also provide the web link here, so you can just click on the PDF slides, then you should be able to download the program from here. Then just follow some instructions. Oh, by the way, so I remember there's no although the Java should be running on the cross platforms, not only in the Windows, but I remember that there's only Windows version here. So if you have a Mac OS, probably you can still find other solutions. But here in the Windows systems, we can just directly install these setup files, and you will eventually get these icons on your desktop. So this is an executable program. You can download from the GAP website by the Academia Sinica, Dr. Chen Ho. Okay, so this is the screen of the GAP. So in the slides, I'll just show you what's the kind of the visual results of this software. So this is the initial screen when you fire up the program. Then you can see there's a file, view, data, gap, graph, configure. It seems very complex, but no worries. The first thing always is that to import data into the program. So just click on the file and open, and then you should be able to import the data. So I just want to show you in the real case. And so we can do this in a more visualized way. So I just fire up the program on my desktop. So I just click on the file and open data. Okay, so there's a tricky part here because the GAP seems to be working very well on the tab delimited text. So it cannot, you usually cannot import the Excel file directly into this program. I don't know why, but the program is also always a very complex job and task. So in this software, the input file should be a text file. So how to do this? And in the course file, if you are able to find the dementia MPI data here, you just open this one, and then you can save the file as the tab delimited file here, which is this one. Then you can just click on save and click yes. Okay, just keep on click yes, and so you will save. Find that in the folder you have one more file just in the text files, then show you the data in the ASCII format, but it's separate by the tab. Okay, so back to the GAP software. So if we open the data, then we just find out the location of our file. So just quickly switch to my folders, and you can see that there's a dementia mpi.txt here. Then so just click on this file and open this one, and you can see that there's a definition of row name and column name here. Because we have the column name, just click on the column name, meaning that we will assign the name of the column by the first row. And because we do not define the row or case name, so we just skip on this row name. Just click on the OK, then you will see it's just successfully import the data into the gap. Okay, so you will automatically assign the row name here from the R0 to the R29. In total, there are 30 cases. So next step is just click on this button, the gap button. Then you will see a definition of the data type and the proximity measure, which is a distance measure. So okay. So here we have the row data. We do not have the distance or similarity data. But if you do have a similarity data, you can just click on the proximity metrics. But here we have to have a row data. And because we have a row data, then we need to define what is the distance. So the distance is kind of the opposite of the similarity of our correlations. So in this case, we just use the correlations as our proximity measures. And of course, you can also use the Euclidean distance or Kendall-Stauss correlations or Spearman's correlations and non-parametric measures or other methods called city blocks or something else. Okay, so you should also notice that here you cannot only do the clusterings on rows, but you can also do clustering analysis on columns. So here we can just do both. Okay, so just click on OK, and we should be able to see. Let me do this again. Okay, so row data and column preprocessing. Yeah, so we can see the results here. So in the first glance, it seems not very nice because you didn't see any dendrogram here. I just see lots of colors. But I just should explain to you because these block show you the colors or codings or values of original data matrix. So just ranging from 0 to 68, and perhaps we should exclude the first MPI total because we want to see more profiles according to the first one. But anyway, just for the demonstrative purpose, I just input all data here, but I encourage you to just look only at the 12 items here. And according to this data, you can just classify this data into its original orders. So there's no clustering here. It just shows the original orders of the data. Now you can also see this in this tab, is original orders. So we can do some clustering analysis here. Just click on this drop-down box, then click on the complete linkage, and also this complete linkage, then click on update. So you can see the result of clustering analysis. So it seems that it's quite similar to our hierarchical clusterings, but you can also see that how these symptoms are clustered together. For example, the depression is clustered with the apathy, irritations, and total scores, meaning that depression is really an important component of the MPI total scores. And also there is this inhibition clusters with the agitations, which is very reasonable, and also hallucination is clustered with the delusions, which is also very reasonable. And also, for example, the aberrant behaviors, nighttime problems, sleep problems, and euphoria, these are all more close to the physiological functions and psychosis. Anyway, So you will expect that if you have more cases, you will derive a more reasonable cluster. In this case, you can derive the symptom profiles into the psychotic domain and the mood domain. So psychotic domain including these sleep or psychosis symptoms, and the mood domain including these blocks, including the anxiety, depressions, agitations, irritable behavior, something like that, else, etc. Okay, so again, in these parts, the clustering of the cases may be not very intuitive at this scale of the 30 patients, but I will expect the clustering is more reasonable or more meaningful when you have more cases. So that is a result of clustering analysis. You can try to control or to make this graph prettier. For example, you can just zoom this clustering, so you can just try to copy and paste to your papers, and you can define the range, you can define the neighbors, something else. So there are lots of functioning in the GAP software, but at the same time it's also very convenient to visualize your results. So I would recommend you to try this software if you want to do the clustering analysis. Okay, so back to our slides. I already put some important steps in the slides, so you can see that how to select the data type and the proximity measures, then give you a glance about the results. So I hope you can enjoy this software to derive some real meaningful results based on your own data. So okay, so this workshop will conclude this 2 weeks course that we focus on the clustering analysis, and which is also called unsupervised learning, because in the unsupervised learning, there's no prior knowledge about the classifications, and we just want to classify the data based on the features. So that is totally different from the classification task or supervised learning. And although we only spent 2 weeks to explore this topic, but I encourage you to read more on the internet resources, because in some medical applications, for example, the clinical trials, then you probably want to use the unsupervised learning to identify the subgroups of the patients and to identify if there is a difference in the treatment efficacy from one group to the other. So that is one of the important applications you need to know in this intelligence healthcare course. Okay, so let's conclude this workshop, and we will see you in the next course. But before we ending this one, I just want to give you the EEG data. So the EEG data, because it's very complex and it requires knowledge about the biomedical signal analysis, and also for the IRB reasons, I cannot give you the raw EEG data. But I already compiled a EEG power calculation results from these O1 channels, which means that we measure the electrical activities from the occipital regions we name as O1. So this diagram show you the 10-20 EEG representations. So usually we'll put 19 electrodes on the scalp and to measure the electric activities from different parts of the brain. But remember, these measurements do not have as good spatial resolutions, because it measures the large area of the electrical activities. But here you can find the results of the power calculation in the O1 data. And because this is not the course of the biomedical signal analysis, but for your reference, I just show you how to convert the time domain data into frequency domain data. And this frequency domain data can help us to do the clustering analysis, because the time domain can vary from the time length and sampling frequency, but the beauty of the conversion is that we can use the Fourier transform to convert the time domain to the frequency domain, meaning that we can find out the frequency components of this data. So immediately you can see that there are some oscillations in this time domain data, which is the real EEG signal. And then you can see there's a certain frequency of oscillations. Then using the Fourier transform, we can identify, okay, this oscillation is around the 9 Hertz. And there's also low frequency components in this data. So that is very useful because we have also a small peaks here, means that we have oscillation in the 20 Hertz. So using the Fourier transform, we can convert any time domain EEG signals into the same frequency domain signal. So that is the basis of the clustering analysis. Again, so this data is also the within the class data, so it cannot release to the public. And but I already compiled the data that can have a frequency range from the 0.6 Hertz to the 30 Hertz. So I encourage you to use this data to do the clustering analysis. And you might wondering that what's this all about, because you can classify the patients based on the questionnaire data. Then the other point is that you can also classify the data based on the EEG markers. So as I said, the type of the data will determine what's the results of the clustering. So if you cluster the patients based on the EEG markers, you should expect there may be some difference in the MPI profile between different clusters. But if you just classify patients based on the questionnaires, then you should also want to validate these clusters by the EEG markers. So that is also depends on what's your applications and what's your hypothesis. Okay, so because we need to conclude this workshop, so I think that you can working on the EEG data just based on the previous knowledge. You can do this very well. So I hope you enjoy this data and course, and we will focus more on the deep learning and convolutional network in the next few courses. Okay, thank you very much. Bye-bye.